So from this video, we're going to start with the chapter of elasticity or properties of solid. Okay. So before starting that chapter, there are few questions that I have to address. Okay. So this is a lot of questions that I'm getting is, sir, how to solve erodov, or when do you solve erodov, or is erodov necessary? Okay. The main question is erodov necessary or that kind of thing. So I'll explain this thing in a very simplified manner. So first, let's define what is inside erodov. Okay. It's a book based on problems. There are a lot of problems. Okay. And the nature of problems are very difficult. Okay, so it's a calculus based problem based book. Okay, and the nature of problem is in mechanics, in electrodynamics. So those two chapters are the toughest. I mean, rest of the chapters there are more or less simplified versions, not simplified versions. So, okay, okay, and okay. Now the nature of problems. It's very calculus based problems. Okay, calculus based problems. See, not all problems are calculus based. First, 20 to 30% of the problems are calculus based. Okay, from your okay. Now, the first thing, the difficulty of the book. It's difficult, genuinely difficult. Okay. Now, see, the requirement. It absolutely depends upon your level of preparation and your rank on your capability. See, I'll tell you something very sincerely. You have to manage your three subjects: okay? Physics, chemistry, and maths. Okay. So, see, and your dedicated rank. See, if you are aiming above 1,000 or 5,000, or if you just need to qualify JW Advanced, I don't think that this is a necessary book. But if you are aiming for a very good rank, okay, this book is very much necessary. Rest assured, this book is one of the fundamental. See, what I'll say is, see, even though calculus is tough, what we teachers started doing is that we solve the calculus, we made a short formula and made you memorize those formulas. So those formulas can appear or is very useful in common type of problems, but the common type of problems that you attend is attended by rest of the Indian students. No? So rest of students that are appearing for competitive exam. So you don't have that edge over others. So although calculus and these are tough, okay, you have to go through it. There is no other way. Okay, you cannot skip it and say, okay, I'll manage. If you want to manage, your rank will, be in that management category. So देखो रैंक नहीं आने वाला है, ठीक है. रैंक मतलब उतना अच्छा नहीं आने वाला है जितना मतलब ये कर. तो इरोडोव क्या नेसेसरी है? बिल्कुल हाँ, ठीक है, अच्छे रैंक के लिए. प्रॉब्लम क्या है? प्रॉब्लम ये बहुत डिफिकल्ट है. तो तुम अपना मतलब नॉर्मल क्लासेस की थ्योरी से इसको डायरेक्टली सॉल्व नहीं कर सकते, ठीक है. तो इसके लिए थोड़ा रेजिलियंस चाहिए. तो अच्छा, तो सबसे पहला सवाल, मैं यूरोप कब शुरू करूं? व्हेन टू स्टार्ट यूरोप, ठीक है. अगर तुम्हारा 70 to 80% ऑफ नीट क्यूआईक्यू खुद से हो रहा है, ठीक है, पहला चेकलिस्ट है. दूसरा चेकलिस्ट है 50 to 60% ऑफ जेडब्ल्यू पीवाईक्यू खुद से हो रहा है. जेडब्ल्यू पीवाईक्यू खुद से हो रहा है, तब तुम यूरोप शुरू कर सकते हो, ठीक है. ये मतलब ये होगा परफेक्ट टाइम टू स्टार्ट यूरोप, ठीक है. व्हेन टू स्टार्ट यूरोप, व्हेन टू स्टार्ट यूरोप, ये हो गया परफेक्ट टाइम, ठीक है. इसके बाद ये वाला नेचर ऑफ यूरोप और नेचर ऑफ यूरोप, ठीक है. अब प्रॉब्लम इसको करे कैसे, ठीक है. देखो हाउ टू डू इट और हाउ टू डू इट. देखो एक चीज तुमको बहुत चाहिए, वो है रेजिलियंस, ठीक है. देखो यूरोप के बारे में मैं एक चीज बता दे रहा हूँ कि वो देखो कॉन्सेप्चुअली बहुत इंपॉर्टेंट है. यूरोप का हर एक सवाल कॉन्सेप्चुअली बहुत इंपॉर्टेंट है और मतलब कॉन्सेप्चुअली आता भी है, ठीक है, बार बार रिपीट भी हुआ है. पर यूरोप का जो लैंग्वेज है वो हम लोग कॉम्पिटिटिव एग्जाम में ज्यादा यूज नहीं करते. डू नॉट यूज द लैंग्वेज ऑफ यूरोप इन कॉम्पिटिटिव, इन आवर जेडब्ल्यू कॉम्पिटिटिव एग्जाम, ठीक है. तो हम लोग वी यूज मच सिंप्लीफाइड लैंग्वेजेस, okay, and that's that. Okay, so in best way to approach these books is take your teacher or go to your teacher and understand the link between problems and the theory that you have read. See, one more thing that I'll say: the theory that is taught in classes is very simplified. Okay, they are not up to Euro. So certain questions can introduce new theory, and that's absolutely normal. Okay, so take your teacher, go to your teacher, try to solve that problem, and try to link it with theory. If theory does not exist, make a theory, okay, or take that solution as a theory and write it in your notes. Understood? So go to your teacher, go to your teacher, Okay, then the main problem is the link between the problem and your theory. Link the problem and your theory. Okay, if certain times in classes you do not give those advanced type of theory inside classes. Okay, so if certain problems contains new type of theory, just write it in the side notes. Okay, so these are kind of advanced preparation that you that will give you a very good competitive edge. Understood? So link the problem in your theory. Okay, sir, my teacher does not help me. See, he might be very busy or kind of thing, so I'm not going to that. Okay, so can you do erodov by yourself? Obviously, you can do. But the amount of time it will take is very unfruitful. Unfruitful means you have to balance three subjects: physics, chemistry, maths. Okay, suppose you are wasting your entire week on physics. That is not the way to take your preparation. Okay, the best way is give every day 1 hour to 3 questions. Okay, and so this is the theory I've learned. Okay, so how is this related to my theory? Acha, this is problem is related to this theory. So this is the fundamental of this theory. Okay, and then you start developing your physics up to a very good standard. Understood? Okay, and that's all. Okay, so if you want to solve your Erodov, go to your teacher. Okay, the link between the problems and your theory is the main thing that you must understand. When to start it? If you can solve 70 to 80% of NEET QIQ and 50 to 60% of JEE QIQ, then it's a very good time to study Erodov. Okay, and is it necessary if you want your rank below 200 or 300? If you have that kind of preparation, it's absolutely necessary. Okay, will it give me a competitive edge? Obviously, definitely, there's no doubt about that. So what's the problem if I skip Erodov? There will be no problem if you skip Erodov. Okay, there's no problem kind of thing. There are many ranks that I've seen. Okay, that haven't even touched them, but you cannot expect a very good rank by avoiding these two. But see, one of the fundamental things, okay, the things that are difficult, okay, that will only give you a competitive edge. Okay, so if something is difficult and everybody is avoiding it, that means your rank, and even if you are avoiding it, that means your rank is in category with everyone else. So if you have to get that competitive edge, start with your okay, and that's it. So let's start, or from next video, not this video, we'll start with the chapter of elasticity or properties of solid. Okay. Now this is the first question. Okay. What is the pressure that has to be applied to the ends of a steel cylinder in order to keep its length constant on raising a temperature by 100 degrees Celsius? So you already know, suppose there is a steel cylinder out here. Okay. Okay. There is a steel cylinder. Okay. If we apply some heat to it, suppose some heat to it is applied. Okay. That means this cylinder will try to expand, isn't it? And what is the thermal expansion? Delta L is equals to nothing but delta L is equals to initial length. Okay. The initial length of the cylinder is nothing but L, initial length into alpha, coefficient of thermal expansion, into change in temperature. Change in temperature means final temperature minus initial temperature. So suppose after applying the heat, suppose I heat it, okay, after applying the heat, it expanded a little. Suppose after applying a heat, this block or this cylinder expanded somewhat like this. Okay, so this change in length, so this delta L is nothing but this one. Okay, initial length into alpha into delta T. Delta T is nothing but final temperature. Final temperature minus initial temperature. Okay. Now my first question is, if I hit an object, it will expand. Okay. Now suppose I press this object and keep hitting, will it expand? No. I'm pressing this very tightly. Okay, I'm pressing this very tightly and hitting it. It has no room for expansion, no? So even if it does not expand, okay, it will develop some thermal stresses. Okay, the question is asking what is the value of that thermal stresses. Okay, so value of thermal stresses. First, we have to figure out what is thermal strain. Thermal strain. Thermal strain is nothing but amount it would have been expanded. Okay, if no external pressure was there. That means L alpha delta T divided by initial length. Okay, so thermal strain is nothing but alpha into delta T. And what is thermal stresses? Stress is nothing but a stress by strain is equals to Young's modulus. So stress is nothing but Young's modulus into strain. Okay, so stress is nothing but Young's modulus into strain alpha delta T. Okay, delta T is nothing but 100 out here. See our question. Delta T is given as 100. Okay, alpha is property of a cylinder. Young's modulus is also property of a cylinder. One important conclusion that you have to note out here is strain or thermal strain. Okay, or stresses, thermal stresses only occurs if they are constricted expansion. That means if you are heating, okay, and if you are closing it, that means if you are heating and you put some pressure, then only thermal stresses will appear. If I keep this block in an open space and keep hitting it, it will obviously expand, but there will be no thermal stresses out here. Okay, So note out here, or the trick out here is thermal stresses, right now, thermal stresses only occur when there is when there is restriction in expansion, restriction in free expansion, in free expansion. That means if this cylinder was kept out here, okay, and there was no external force, this cylinder was allowed to expand under heat. Okay, it would obviously expand, but there would be no thermal stresses in this cylinder. Thermal stresses only occurs when you constrict the expansion or when you try to stop the expansion. Understood? So this was the first question. Okay. Now in this question, what is the internal pressure in absence of an external pressure that can be sustained by a glass tube by glass spherical path? That means what is this question trying to say? See, part A of the question is saying there is a hollow glass tube, okay, or hollow glass cylinder, okay, and this is hollow part. Okay. And inside this glass cylinder, there is some gas kept out here. Okay. Now, what happens if I keep on increasing the pressure of the gas? Suppose I can increase the pressure of the gas infinitely. So if I start increasing the pressure, after a certain while, this cylinder will leak open or burst open. Okay. So my question is asking at what internal pressure of the gas will this cylinder burst open or will this cylinder fail? Okay. So there is a very easy way to analyze this. Okay. So suppose this was locked. Okay. This surface was locked. This surface was locked. Okay. I'll be analyzing my cylinder from this plane. Okay. Or from this plane. Okay. Okay. Now suppose this was a cylinder. Okay. I'm rotating this cylinder like this. Okay. That means I'm seeing the cylinder from forward or front. My cylinder will look somewhat like this, isn't it? The gas is inside. And this is my cylinder, isn't it? Gas is inside this portion. Okay. Achha, one more thing. Let me draw the cylinder a little bit thick. Okay. Let me provide some space for the gas. This is my cylinder. Okay. And this is gas. Gas is inside the cylinder. Okay. Okay. Now, to analyze the pressure inside the gas, okay, or pressure inside the cylinder. Okay. And what I'll do is I'll cut this cylinder in half. Only for analysis. Okay. It's not that I'm cutting the cylinder in half and letting the gases escape. I'm just analyzing. Okay. This much thickness is nothing but T, or thickness of the cylinder wall. Okay. Okay. This is the radius of the cylinder. And one more thing in this type of problem, you have to assume that this thickness is very much less compared to R. Okay. So thickness is very less compared to R. Understood? So this is our primary assumption. Okay. Now suppose gases was out here. Okay. So if gases was out here, my first question is, what is the force by gases? Or how do we solve this problem? See, in order to solve this kind of problem, we just have to equalize pressure forces is equals to tensile forces. Remember soap bubble that we have solved in surface tension? This is the same category of problem, okay, of that soap bubble. That means the gases inside will apply pressure like this. Okay, suppose let me draw this figure. Okay, and this is the thickness. This. Okay, the gases will apply pressure like this. Okay, and the cylinder will try to pry open. And what is holding the cylinder back? The tension forces from the cylinder wall. These forces is holding the cylinder together. Okay, so this is nothing but pressure forces. This is nothing but tension forces. So my main equation would be pressure forces is equals to tension forces. Pressure forces is equals to tension forces. Okay. Now my first question is, what is pressure force? In soap bubble, what do you do? Pressure inside into pi r square or you have 4 pi r square? It should be pi r square, no? Why? Projected area, isn't it? So what is the projected area of this cylinder? That means if I shine a torchlight from here, suppose if I shine a torchlight from here, okay, and I take my projection in this plane, what is the area of shadow in this plane? Okay, that is my projected area. And why I'm doing like this? See, this component or the horizontal component of this pressure force will cancel out the horizontal component of this pressure force. No. So what I'm doing is I'm taking the projected area out here. Okay, and pressure force is nothing but pressure into the projected area out here. Understood? So the projected area is nothing but, see, projected area out here would be nothing but R, not out here. Okay, the projected area from this portion, and from this portion. Between these two portions only pressure force is acting. So this area is nothing but, see, 2R or twice the radius into length of the cylinder. See, 2R into length of the cylinder. So 2R into L. Understood? This much is understood. So pressure forces is nothing but pressure into projected area, and pressure forces is nothing but in upward direction. Okay. So P inside into 2RL. What is tension force? Tension force is nothing but stress into contact area. So how much is this much contact area? This much contact area is nothing but thickness into L. So stress into thickness. Thickness is nothing but 2T. Why 2T? This T and this T. Twice T into length L. A length L is nothing but the length of the cylinder. Okay. And cancel out the LL. Okay. Cancel out the 2 and 2. So our pressure at which the cylinder will fail is nothing but sigma T by R. Sigma T by R. Okay. So this is our first question. Okay. First part of the question. Okay. One more thing. The wall thickness that I've used out here, T, is given by delta R. Okay. The radius R, okay, or R out here is nothing but 25 millimeter. Okay. So instead of using T, they have used delta R. Okay. Now the second part of the problem. How do I solve the same scenario if instead of using a cylinder, I'm using a spherical flask? Okay. So let's take the second part. Spherical flask or spherical container. Spherical container. Okay. So suppose this is a spherical container. Okay. And somehow, see, this is a spherical. This is a spherical container. Okay. And the container has some walls. No? So suppose I'm taking my container. This is a spherical container. Inside this gas is there. Okay. This is the thickness. This T is nothing but thickness. This T is nothing but thickness. Okay. Now my first question is, if I divide the cylinder, if I divide the sphere into half, my diagram would be nothing but this, somewhat like this. Okay. The same type of problem. Okay. Tension force, and pressure force, pressure force, pressure force, pressure force. Now my question is, for a sphere, what is the projected area? That means what is this much area? What is this much area? See, while calculating surface tension in a bubble, okay, or pressure inside a bubble, what is the projected area of the sphere? Because pi r square, no? That means if you take this sphere, okay, and if you shine a light through it, if you shine a light out here, okay, and you are taking the shadow, okay, shadow in this plane, the area of the shadow would be nothing but pi into r square. The area of the shadow is nothing but pi r square. Understood this much? And if I do my calculation for pressure force, PRE, pressure force is equals to surface, not surface tension force, tensile force. Pressure force is equals to tensile force. Okay, so what is pressure force? Pressure force is nothing but P inside into projected area pi r square. What is tension force? Sigma into what is the area of this portion? Okay, this portion is nothing but 2 pi r into T. 2 pi r into T. What is the area of a ring? 2 pi r area. Sorry, 2 pi r into T. Okay. What is the area of a ring? 2 pi r dr. So instead of using dr, I'm using T. Okay, okay. Understood? Simple, straightforward. Okay. 2 pi r T, the area of the ring, the area of this entire ring. Okay. That means if you take this sphere out here, open it like this, the thin that this much area, okay, will be nothing but 2 pi r perimeter into thickness. Understood? And let's cancel out this one, pi r square, pi would get cancelled. So my pressure inside, or maximum allowable pressure inside, is nothing but 2 sigma T by R. Okay, this is the maximum allowable pressure that is inside. So this was on part 2 of the question, where you have to balance out the pressure forces and tensile forces. Okay, so now let's move on to the third question. So in this question, let's understand the question first. In this question, there is a axis of rotation. Okay, and in this axis of rotation, there is a horizontal rod out here. Okay, and this rod is rotating with angular velocity omega. Okay, the length of the rod is L. Okay. Now the question is asking at what value of angular velocity omega will the rod fracture? Okay, so suppose, let me modify this question a little bit. Okay, so suppose there is this kind of setup. Okay, so let me draw the setup first, then I'll show you the setup. Now suppose there is this kind of setup. Okay, this kind of setup means there is a lot of small block M or dm elemental mass, and each of these mass are connected by threads, and the entire system is spun around with angular velocity omega. Okay, The first question that I must ask you is where will this or which one of these thread will be set apart? Okay, or which one of these thread will first break? By common sense, you can easily observe that this thread or the thread that is at the center, this will be set apart. Why? Because this thread is holding all these blocks, isn't it? So this thread or this thread, okay, is holding all these blocks together. Understood? Now suppose I want to say, why is this thread being itself apart? Due to tension force. So if I want to calculate what is the tension force, so suppose tension force on this thread, okay, tension force on this thread is nothing but m omega square r plus m means this mass into omega square this much r. So plus this much into omega square this r plus this much r m this much mass into omega square this much r. So if I do the same thing out here, what I'm trying to do, just observe. Instead of this small block, I'm taking an elemental mass dx, okay, of distance x from the thing. So tension force is nothing but each of this elemental mass into omega square m omega square into r. The value of r is nothing but the distance of the elemental mass from the axis of rotation. Out here the value of r is nothing but x. Okay. Now if I add up all these masses, okay, if I add up all these masses, what will happen? I'll get the tension force out here. Similarly, if I integrate this one, I'll get the tension force out here, isn't it? So if this rod is spun around, the rod will break from the middle. Okay. So tension force, total tension force is equal to dm omega square x. Now suppose I have the entire mass of the rod as m, entire length of the rod as L. What is the mass of element dx? I can easily say whatever is the linear density of the entire rod, that will be the same linear density of this element. The density, the rod is made of the same material. So whatever material this entire rod is made up of, this element will be made up of the same thing, isn't it? So suppose if I do like this, lambda or linear mass density is equals to mass divided by entire length. Understood this much? Which is equals to elemental mass of the mass of the element divided by length of the element. I can easily say that dm, or if I take these two equations, I can easily say dm is equals to m by l into dx. Understood? Now what I do is, if I substitute this dm out here, okay, I'll get my tension force throughout the rod. Okay, so tension force is nothing but m by l into dx into omega square x. And if I integrate that, the total tension force at the center of the rod is nothing but m by l omega square x square by 2 x dx. Integration of x dx is nothing but x square by 2. What is the upper limit and lower limit? Upper limit is nothing but from this position x is equal to 0 to lower position is nothing but x is equal to L by 2. So from 0 to L by 2. So tension force is nothing but m L omega square into L square by 4 to the 8. So L by 2 whole square. L square by 4 into 2. 8 minus 0 square by 2. So it's L square by 8. So total tension force out here is nothing but, I'll write this value out here, or this value which I obtained out here. Okay, m by L omega square L square by 8. Write L square by 8. So tension force is nothing but m by L omega square L square by 8. If I cancel out the L square and L, I'll get tension force is equals to m omega square L by 8. Simple enough. Now this tension force is causing this thread to rip itself apart. No? So similar kind of thing will happen out here. This tension force will only rip this rod apart. Okay. Now if I say, okay, stress. See, every material does not. Every material has a fixed amount of stress. Okay. So can I relate stress and tension? Obviously, stress is equals to tension into cross sectional area. Okay, or cross sectional area of the rod, or this much area of the rod, or if you look the rod from this side, the exposed area of the rod. Understood? So tension force is nothing but sigma by K. Now I just substitute this value. Okay, this value of tension out here or out here. Okay, both will have the same result. This tension will be substituted out here. Okay, so tension force or sigma by A is nothing but m omega square L by 8. Okay, so sigma or whatever or omega square is nothing but, bring the rest of the term out here. Omega square is equals to 8 sigma by MAL. MAL, or omega is equals to, see, if omega square is equals to this much, omega is equals to nothing but under root. Okay, so 8 sigma by M into A into L. Fair and fine. There is one more method or shortcut method of way of doing it. See, lot of you hate integration. Okay, and I'm repeatedly saying, do not hate on this integration kind of thing, because see, this integration, do not hate on this integration kind of thing, Okay, they'll only be the one that will be the differentiating factor between you and toppers. Okay, so forget that. Let me teach you the shortcut. The shortcut is nothing but, see, out here. Okay, whatever is the tension force. Okay, m omega square r. Tension force is nothing but m omega square r. Okay, now if I take this mass, okay, situated at the center of mass, that means the entire mass would be nothing but m by 2, situated at l by 2, sorry, l by 4, because if this entire distance is l, this distance is l by 2, and half of this distance is l by 4. So this entire m by 2 situated at l by 4. So I can easily get tension force is equals to m by 2 omega square, situated at center of mass. Center of mass is nothing but l by 4. L by 4. So tension force is nothing but m omega square L by 8. M omega square L by 8. And you get the same answer out here. And you get the same answer by integration. Okay. So this was kind of shortcut, but follow through the integration process. Okay. It will be beneficial for you. Okay. Now this next problem. This next problem is same as the problem that you have done in surface tension. Okay. So what this problem says is that there is a ring of, okay, and this ring is rotated about the center axis with angular velocity omega. Okay. At what angular velocity? Okay, at what RPS will the ring rupture or will this ring break? So obviously, how do you analyze this kind of thing? We have already learned in surface tension. We take two lines out here. Okay, we take two lines, and this out here is nothing but the element. And suppose if I draw the element out here, I'm drawing the element out here. Okay, this is the angle to the center of the circle. Okay, if I cover this one, okay, this is d theta by 2. This is d theta by 2. Okay, understood? Or let me make it clutter free. This entire thing is d theta. Okay. Now, where will be the tension forces? Tension forces will be along the ring. This is tension forces. This is tension forces. Okay. And while rotating, if this is rotating like this, okay, in what direction is the centripetal forces? Sorry, centrifugal forces. Centrifugal forces will be in opposite direction. See, I'm analyzing. I'm saying centrifugal forces. A lot of you might say centrifugal is a pseudo force. Obviously, it's correct. But try to analyze. See, because something must keep this block or something must keep this particle rotating in a circular orbit, no? Okay, that is the force that is being applied by this tension force. Okay, so instead of using that kind of means dynamic analysis, I'll be keeping this static and I'll use centripetal forces. So centripetal forces is in this direction, isn't it? And what is the value of centripetal forces? Mass of this much of element into omega square into r. R is nothing but how far is this element from the axis of rotation. So mass into omega square into r. Now all I have to do is I have to balance out the vertical component of force, because in horizontal component this horizontal component of tension force and this horizontal component of tension force already balances out each other. So balancing vertical component of forces, balancing vertical component of forces in upward direction is dm omega square r. Upward direction is nothing but dm omega square into radius. Now the vertical component of this tension forces. What is the vertical component of this tension forces? Suppose if I draw a line out here, okay, and I draw a same vertical line out here. Understood? I just drew two vertical lines out here and out here. Now, if I say, okay, hear me carefully out here. If this entire angle is d theta, this much angle is nothing but d theta by 2. And this is nothing but a parallel line. So if this is d theta by 2, this is also d theta by 2. Understood? So if this is d theta by 2, this line and this line forms 90-degree angle. And if this is d theta by 2, this is nothing but 90 minus d theta by 2. Isn't it? So I'll write this angle as 90 minus d theta by 2. Or I'm writing theta by 2 dash. Whenever I write dash, is nothing but 90 minus d theta by 2. Okay. So the vertical component of these tension forces is nothing but t cos theta by 2 dash, or t cos 90 minus theta by 2, or t sin theta by 2. So 2t sin theta by 2. Now this is our entire premise of the problem. Okay. And our problem is already solved. See, if the entire mass of the ring is m, okay, let's see, this is ring or this ring. If the entire mass of the ring is m, okay, so if I write, okay, linear density of the ring is same as linear density of the element. So linear density is equals to m divided by length of the entire ring 2 pi r, which is nothing but dm elemental mass divided by how much is this much length. This much length is nothing but r d theta. So r d theta is nothing but this much length, r d theta. Okay, r and r will get cancelled. If I take this two equation, okay, r and r will get cancelled, and I'll get m by 2 pi is equals to dm by r, or dm is equals to m by 2 pi into, sorry, not r and r is getting cancelled, d theta, m by 2 pi into d theta. Now if I substitute this value of m by 2 pi into d theta out here, I'll get my answer. Okay, and whenever this type of problems come out, let me write it first. Okay, m by 2 pi d theta omega square r is equals to 2t sine theta by 2. Okay, now one thing you need to remember whenever this type of ring problems comes up. Okay, see, you have to approximate. See, this length is very small. I have told you in surface tension also this will happen. Okay, so if this length is very small, you have to approximate sine theta is nearly equals to theta is nearly equals to tan theta. So for very small angles, theta is nearly equals to sine theta is nearly equals to tan theta. Okay, for very small angle, or very small angles. Okay, so now if I solve the equation, what is it? M by 2 pi. Okay, d theta becomes theta omega square r into 2t. Okay, sine d theta by 2. Also, this is d theta. Okay, this is also d theta. Okay, sine d theta by 2. Sine d theta by 2 becomes d theta by 2. Okay, d theta and d theta gets cancelled. 2 and 2 will get cancelled. Okay, let me erase this. Okay, cancel out one. Okay, what are they left with? So if I send this to the right hand side, okay, or m by pi omega square r is equals to 2t. Okay, and let me just modify a little bit. Okay, okay, okay. Now my question is asking at what RPS it will fail. That means I have to find out the value of omega square. Before finding out the value of omega square, I must substitute this tension force in terms of sigma or in terms of stress. So tension force is nothing but sigma into A, isn't it? Tension force is nothing but stress into cross-sectional area. That means cross-sectional area of this thing. That means if I look this thing from side, whatever is the cross-sectional area. Okay, so let me substitute this out here. T is equals to sigma into A. So if I substitute this value out here, I'll get m by pi. M by pi omega square r is equals to 2 into sigma into A. Okay, and I have to isolate the value of omega square. Omega square is equals to 2 sigma A divided by r into pi by m. That's it. Or omega is equals to under root of 2 sigma A by r into pi by m. Okay, pi by m. But that's it. Okay, so this was our question. Understood? Okay, so let's move on to the next question. So this problem is a classic example of how you can use binomial expansion. Okay, so in this question, a steel wire of diameter d of 1 millimeter is stretched horizontally between two clamps. Okay, and a mass is hanged by it. Okay, let me draw the diagram, then we'll explain properly. Okay, suppose there is a wall out here. There is a rope out here, tightly bound. So from middle of the rope, I'm hanging a mass. Okay, this is a diagram. After a certain while, what will happen? This rope will sag, isn't it? Due to this weight. The question is asking, I have to find out the value of x, or how much the rope will sag. So before finding out the value of x, okay, if the entire length of the rope is L, okay, the length of half of the rope is nothing but L by 2. Okay, so let me just draw two L by 2s. Okay, this length is L by 2, and this length is also L by 2. Fine. And now before doing anything or before finding out x, okay, I must first find out what is the change in length. Change in length means final length, okay, minus initial length. What is final length? Final length is nothing but if I use Pythagoras theorem. Pythagoras theorem means base square plus perpendicular square is nothing but hypotenuse square. So final length is this much, isn't it? And final length is nothing but change in length. Change in length is nothing but final length. Final length is L by 2 whole square plus x square under root. This is final length. Length final minus length initial. What is length initial? L by 2. L by 2. Now out here, if I assume, okay, this x is very small as compared to L by 2, then my problem becomes very simple. So if I use binomial expansion out here, how do I use binomial expansion? See, I can write this square root as 1 by 2. Okay, this is nothing but length initial So if I expand this binomially, I can take which is larger. L by 2 is larger. So I'm taking L by 2 whole square as large. Okay. L by 2 whole square outside the bracket to the power 1 by 2 into open bracket 1 plus x square divided by L by 2 square. So x square divided by L square by 4. Okay. X square divided by L by 2 square is nothing but a chart showing L by 2 square. Now this is nothing but L square divided by 4. Okay. L square and 4 will go upward to the power 1 by 2 minus L by 2. Understood? Now this entire thing become 2 into 1 by 2 is nothing but 1. There's nothing but L by 2 into this value. Okay. Let me write the equation little bit left out. Okay. So delta L is nothing but L by 2. So delta is nothing but L by 2. Okay. Into how much? If I expand this by higher binomial expansion is nothing but 1 plus nx 1 plus half into 4x square by L square minus L by 2. So 2 and 2 get out here. So delta L is equals to L by 2 into 1 plus 2x square by L square. Okay, minus L by 2. Fine. Now if I multiply this, delta L is equals to L by 2 plus these 2 and these 2 get cancelled. So x square by L, okay, minus L by 2. This and this is getting cancelled. Or delta L is equals to x square by L. And this is the entire premise of the question. Okay. Now I have got delta L, or change in length is nothing but x square by L. And when I've obtained this, the entire question becomes simple. Okay. Now see, why will the rope come down? Due to tension force. Tension force. If this angle is theta, t sine theta, or 2t sine theta is equals to mg. Isn't it? This is the mean balance. See, for very small angle theta, okay, sine theta is nearly equals to tan theta is nearly equals to theta. So sine theta can be written as tan theta. And tan theta is nothing but perpendicular by base is nothing but x by L by 2. Okay, x divided by L by 2. So if I write this equation as 2t, okay, into 2x by L is equals to mg. Okay, now we must find out the expansion. Fair enough. So stress is equals to Young's modulus into strain. Okay, between the rod. What will be the descent? I have to find out the value of x. So instead of x, if I write down, if I modify this tension as stress into area, okay, stress into cross-sectional area. So 2 sigma A into 2x by L is equals to mg, or 4 sigma AX by L is equals to mg. Fine. What is stress? Stress is nothing but Young's modulus into strain. Young's modulus into strain. Okay, and strain is nothing but change in length by original length. Change in length by original length. So if I write this entire equation, okay, I am writing this entire equation down here. Okay, write this equation. So 4. What I'm doing is I'm writing this equation out here. Okay. So finalized form of this equation is nothing but Young's modulus into strain is equals to mg. Sorry, Young's modulus into 4 into Young's modulus into strain. Young's modulus into strain is nothing but substituted by sigma out here. Okay, into AX by L is equals to mg. Okay, strain is nothing but delta L by L, or 4 Young's modulus into delta L by L, okay, into AX by L is equals to mg. Understood this much? And delta L is nothing but, we have found out delta L is nothing but x square by L. So this value is nothing but x square by L. So my equation becomes 4 gamma into x square by L into L square. This L and this L will become L square into AX by L is equals to mg, or 4 gamma x cube A by L cube is equals to m into g, or x cube is equals to m g L cube divided by 4 into gamma. Achha, m g L cube divided by 4 gamma A. 4 gamma A. Okay, gamma is nothing but Young's modulus. Okay, or x is nothing but m g L cube divided by 4 gamma A to the power 1 by 3. So this question was nothing but this simple. Okay, so this is our final answer. The value of x is nothing but this much. A simplified form of this question might come, but understand the approach. The first kind of approach that we do out here is binomial expansion out here. Okay. And then we keep on substituting the values based on what is asked in the question. Okay. So this was the first of few questions. Okay, first of 4 questions. In the next class or in the next video, I'll upload 5 more questions. So this is how we do erodov. Okay, little by little, we have to understand the link between the theory that I have learned and the problems that arrive. Okay. So, and these problems in erodov are repeated many times. Okay, it's not like the concept, the snippets of concept from erodov, such as the binomial expansion out here, the ring problem out there, is repeated many times in the syllabus. Okay. So till then, bye.